Hello everyone and welcome back to another minute concept, this time about electric potential. Electric potential describes the potential energy of a charge at a certain point, as you can see here. But what does this mean? So imagine that we have two charged plates. Let's say this side up here and this side here. The up the upper is going to be positively charged and the lower is going to be negatively charged. We know that electric fields go from positive to negative, so let's just draw a few arrows going this way. Obviously, if we put a charge here, we can expect it to behave in accordance to whatever the whatever the charge dictates it will do. So for example, if I am going to be making this a positive charge, we know that it should be going this way because positive repels positive and positive is attracted to negative. And same thing, if I make this negative, we know that this is going to repel and it's going to go towards the positive. However, electric potential describes this interaction using a similar concept to work. Now, electric potential energy and electric work are essentially the same. They're related by the same relation as standard potential energy or classical potential energy or mechanical potential energy. So, if you recall in one of our physics 1 videos, we actually have the equation work is equal to the negative change in PE. And we know that work is equal to FD, cos. But we'll remove cosine because it doesn't matter here. We can apply work into our electric potential understanding. First, let's understand how does work behave here. Okay, so we know that there are three cases. We can have negative work, we can have positive work, or we can have zero work. And when we have zero work, that basically occurs when we have displacement that's perpendicular to our force. So, for example, if our charge were moving this way, completely through the electric field, it wouldn't be affected by it, and thus it would be experiencing zero work due to the field. That is zero work. Now, how about negative and positive? This is when it gets a bit more complicated, I guess, but you just have to think about it in a more straightforward manner than you would probably expect. Like I said earlier, we know that, for example, if we make this a negative charge, we know that it's going to be going away. It's going to experience repulsion from this side. So it's going to experience a force going here. However, the field says that it's supposed to be going the other way. So the field is trying to push it this way. It's trying to go here. Now, hold on, let's highlight that with a different color. Let's use yellow. The field wants it to go this way. So the charge is displacing on the top. It's displacing away from the force that it's experiencing here. Or the field, rather. Away from the field, where the field wants it to go. However, the force that it's experiencing is pushing it in this way. So it experiences positive work due to the charges here. However, the electric field has negative work. Why? Because it's displacing opposite to where the field is pushing it. And like we determined about work before, if the force and displacement are going in the same direction, then that's positive work. If the force and displacement are going in opposite directions, that's negative work. So how about let's try a positive charge? Let's try a positive. So a positive charge would be going along the field lines. So it's going this way. Because it's also being repulsed by positive. Right? So overall, it's experiencing positive work. So here is positive work. because the force is going this way, the displacement is going this way. And as for the field is going to be going this way too. So the field is going this way and it's displacing this way, so the field also does positive work. What's the main difference here? It's that for positive charges, going with the direction of the electric field automatically dictates positive work due to the electric field. However, here with the negative charge experiences negative work done by the field because the field is trying to push it somewhere that it cannot be. You can't bring the negative charge closer to the negative side because it's going to be repulsed and it's going to be pushed away. Because it's being pushed away, the electric field does negative work since it's trying to bring it that way, but then it simply doesn't want to be there. And that's pretty much the basics of it. That's how you understand it. So we describe this as the work, right? We know that this is now our understanding of electric work. So how do we relate it to potential energy? We can relate it to potential energy by understanding that the farther the distance between the charges and the side that it's supposed to be in. So for example, oops, let's bring this back. Let's leave this positive charge so it's easier for us to understand. This positive charge wants to go to the negative side. So it's like having a ball thrown up slightly above the ground. Its potential energy isn't that high. It's kind of close to the ground already. Now what happens if I move the ball a bit more upward? Now it has a higher potential energy and the arrow is longer. This arrow is longer, so it now possesses more potential energy. It wants to go down even more. And that's exactly what we're trying to describe. So the higher or the farther away a charge is from where it's supposed to be, that is higher electric potential energy. Now how about in the case of a negative charge? A negative charge, I'll just use blue. Don't want, it looks ugly. Hold on. Here, we'll keep there. So the negative charge is over here. Let's see, there's some force. Well, it's being pushed away, right? It's going here. We know that the negative is supposed to be going to positive. It experiences a negative work, but then it experiences a decreasing potential as well because it's going towards the positive. It wants to be in this side. It wants to be here. If I try to bring it away, then it would increase the arrow and it would have more potential. Now, let's try to understand this again with this new information. Let's try to understand the work and the potential energy now that we understand how it behaves in terms of the distance of a charge and where it wants to be. So, when a charge is far away, that's like lifting it up. When we lift a ball up from the ground, gravity does negative work. So negative work done by gravity, right? And here, we're lifting it up. So it's far away. And there's negative work. Now, how about the potential energy? The potential energy is high. Now, what happens when we lower the distance? Let's make the distance now really close. So we're going to lower the distance and it's going to be right here. Now, the signs will flip. Because now we've decreased our potential energy and we've made positive work because it's going where it's supposed to go. Now, how about the positive charge? The positive charge is far away from where it wants to be. So, it has a high potential energy and it's currently doing negative work. If we moved it up, of course. Like, let's say we're pushing it upwards and it's displacing upwards. That's why it's there. Then negative work. Now, same thing, if I bring it down, it would experience lesser PE, but it would experience positive work. And that's essentially the basic of it. Now, how do we describe this mathematically? Describing potential energy mathematically is straightforward, just as W equals FD. So, about this formula, we have a value for force when it comes to electrostatics. We know that force is equal to K Q1 Q2 over R squared. We know this as Coulomb's law. So now let's try to integrate this with our work. So all we have to do here is just replace this. Now we'll multiply to the displacement. But displacement is a measure of distance, and R is also a measure of distance. So we can say that D can be equal to R. So we'll just replace D with R, and they cancel each other out. So our work, or our electric work or electric potential, is actually equal to just KQ1, Q2, all over R. And positive work is equal to negative potential energy. Negative work is equal to positive potential energy. So this is our formula for electric potential. And you can actually compare this even to our electric field formula. Using the electric field formula, you'd get another form of the work equation, which is just EQR or EQD, which is essentially the same. Now, again, work is equal to negative change in PE, which in this case is electric potential energy. So in other words, if we want to get the EPE, we can just put a negative sign there and then make this positive. And yeah, basically we just mess around with these equations. And solving is quite straightforward. So let's imagine, for example, that we have two charges. Wait, let's bring this with me. Oh, sorry, that's the Gauss law lesson. Let's bring this. Don't mind that. Okay, this is our electric potential. Imagine that we have two charges vertically positioned, and we have a negative and we have a positive here. So let's say that the first one has a value of 2 coulombs and the other one has a value of 3 coulombs, and their distance between each other is 6 meters. So all we have to do here is just plug in our values, and we'd get 9 times 2 times 3 times 10 to the power of 9 over 6. 2 times 3 is equal to 6, so these will cancel out, and we'd get 9 times 10 to the power of 9. And this is our work. Now, what's the unit for work? Joules. Alright, now, how do we interpret this? So basically, between these two, they're going to experience, if they move towards one another, that's equivalent to 9.10 to the power of 9 joules. However, if they're not moving, then right now they have 9 times 10 to the power of 9 joules worth of electric potential energy. So, that just looks like Jeppe. I don't know. Okay, so again, if they're not moving, they possess electric potential energy. If we bring them close to each other, only one side at a time, the work will be equivalent to 9 times 10 to the power of 9. And this relation is because this is equal to negative change in PE. Right? And yeah, so the farther they are, the more work, the less work there is, or the negative work there is. And the closer they are, the more positive the work gets. but the lesser the PE. So that's it. And I hope you guys understood electric potential energy, because really it doesn't get any more simple than that. It's just the distance between two charges and how much they want to be close to each other. It's essentially just a law of attraction when we're just describing the distance between 2 points. Now, how does this come into play in other topics? This is actually a key point for voltage. Voltage is actually potential difference, and voltage is given to us by Ohm's law, which is V equals IR. However, what some people might not remember is that voltage, the ones that we see on our batteries, are actually equal to V is equal to the electric potential over Q. So that's it. And when we have the voltage, we can measure. The voltage is basically a measurement of how much potential a battery, any appliance, or yeah, the distance between the positive and negative ends that run the current through your appliance. And obviously, the larger the battery, the larger the gap between 2 points, so the larger the voltage. That's why car batteries are large, and you can see that they actually have large spacings between their anode and cathode. That's because when you have, for example, your jumper wires, they'll loop around and then they'll go through here, and the reactions that cause the electricity to happen are inside. And that big gap that allows the potential difference to happen, that's what powers your car. That's your car battery. On the other hand, let's say you have a 9-volt battery, the chubby one. It's chubby because you need to make sure that it has enough stuff inside, enough gap, enough material, so that once it's plugged into your whatever appliance, like maybe your flashlight, the loop actually generates electricity equivalent to the amount of, or utilizes electricity equivalent to the amount of voltage that's required. And yeah, so that's basically it. The distance between two charges is very important to electrodynamics, electrostatics, and just in general how much our appliances run. So I hope you guys learned something, and this topic, I hope you guys can wrap your heads around it, because when I studied this the first time, it was a bit confusing, particularly this part. I tried my best to explain it, but if you guys have any concerns or any questions, you guys can leave it in the comments. Maybe if you guys would like one last recap, no? There's different reference points for work. However, depending on your reference point, all you have to do is pay attention to the force and the displacement of your charge. The electric field does work on your charge. However, it's not going to be positive all the time, and it's not going to be negative all the time, depending on the location and the value of your charge. Okay, so for example here, the electric field wants to bring this down, and it's going to go down, so that means that it will do positive work. On the other hand here, the electric field wants this to go down, but it can't go down, so it's going to be doing negative work. So that's literally it. And I hope you guys learned something. Thank you everyone for watching, and I'll see you all in the next video about AC and DC. So thank you everyone, and goodbye.